Hello there. Now that we've covered the fundamentals of the factory method pattern in our previous lesson, it's time to put that knowledge into practice. Today we're going to implement a complete vehicle manufacturing system that demonstrates how to apply this powerful design pattern in real-world scenarios. We'll build upon the concepts you've already learned, creating objects without tight coupling to specific classes, and show you how to structure a robust, scalable factory system. By working through this hands-on implementation, you'll see exactly how the factory method pattern solves common object creation challenges. You'll also discover how it makes your code more flexible and maintainable. Now we can dive into building our vehicle manufacturing system and see the factory method pattern in action. We'll begin our journey by exploring the foundation of our factory method pattern implementation, the vehicle interface. This interface acts as a blueprint that ensures all our vehicle types follow the same contract while still allowing each vehicle to have its own unique behavior. I have already created a vehicle interface inside our factory method package. This interface is going to define 4 essential methods that every vehicle must implement. Think of this as establishing the rules that all vehicles in our system must follow. First, I'll define the start method. This is a void method that handles powering up any vehicle. Whether we're turning on a gasoline engine or initializing an electric motor, every vehicle needs a way to start up and get ready for operation. Next, I'll add the stop method. This ensures that every vehicle can come to a safe and controlled halt. Just like starting, every vehicle needs its own way to shut down safely, whether that's turning off an engine or powering down an electric system. Then I'll include the accelerate method. This method determines how each vehicle increases its speed. Some vehicles might have smooth automatic transmission acceleration, while others might deliver instant electric torque. The interface ensures every vehicle can accelerate, but each type can do it in its own unique way. Finally, I'll define the get specifications method that returns a string. This method provides technical details about each vehicle, such as the number of doors, seating capacity, and engine type. It's like having a specification sheet that describes what makes each vehicle special. With these 4 methods defined in our vehicle interface, we've established a solid contract that ensures consistency across all our vehicle implementations, while still allowing for unique behaviors. Now that we've established our interface foundation, we can bring our first vehicle to life by creating the sedan class. I'll create a sedan class that implements the vehicle interface. This class will demonstrate how we can implement our vehicle interface to create a specific type of vehicle with its own unique characteristics. By using the implements keyword, I'll tell Java that this class must provide concrete implementations for all 4 methods we defined in our interface. I'll start with the start method implementation. For our sedan, I'll print a message that says, sedan starting the gasoline engine. This will immediately tell us that our sedan uses a traditional gasoline engine, which distinguishes it from other vehicle types we'll create later. Next, I'll implement the stop method. Here I'll print, sedan stopping the gasoline engine. Notice how I'll maintain consistency with the start method by emphasizing that this is a gasoline-powered vehicle. Now for the accelerate method implementation. This is where our sedan will really show its personality. I'll print sedan smooth acceleration with automatic transmission. This will highlight one of the key comfort features that sedans are known for, which is that smooth, refined driving experience. Finally, I'll implement the get specifications method. This method will return a string that says, sedan specs 4-door, 5 seats, gasoline engine. These specifications will clearly identify our sedan as a family-oriented vehicle with conventional fuel technology. What'll be beautiful about this implementation is that our sedan class will now fulfill the vehicle interface contract completely. Every method will be implemented, but each one will reflect the unique characteristics of a sedan vehicle. This is the power of polymorphism in action. Building on what we've just accomplished with our sedan, I'll create our second vehicle type by implementing the SUV class. This will demonstrate how different classes can fulfill the same interface contract while maintaining completely different behaviors and characteristics. I'll create a public class called SUV that also implements our vehicle interface. Just like with the sedan, I'll need to provide implementations for all 4 required methods, but this time I'll give them behaviors that reflect what makes an SUV special. Starting with the start method, I'll print SUV starting the powerful engine. Notice how I'll emphasize the power aspect here, which will be quite different from the sedan's focus on the gasoline engine type. This will show how the same method can have completely different messaging based on the vehicle's characteristics. For the stop method, I'll print SUV stopping the powerful engine. Again, I'll maintain consistency with the start method by emphasizing the engine's power, which will be a key selling point for SUV vehicles. The accelerate method is where our SUV will really shine. I'll print SUV strong acceleration with four-wheel drive. This will highlight the SUV's capability for both power and traction, which sets it apart from our smooth accelerating sedan. Finally, the get specifications method will return SUV specs 5-door, 7 seats, all-wheel drive. These specifications will show that our SUV is designed for larger families and challenging driving conditions, with that all-wheel drive capability being a standout feature. This SUV implementation will perfectly demonstrate polymorphism in action. Both the SUV and sedan will implement the exact same interface methods, but each will provide its own version that reflects the vehicle's unique role and characteristics. Now we'll take a step into the future by creating our electric vehicle class. This implementation will demonstrate how our factory method pattern seamlessly accommodates emerging technologies while maintaining the same consistent interface structure we've established. First, I'll create the electric vehicle class. I'll start by declaring a public class called electric vehicle. Next, I'll add the implements keyword followed by our vehicle interface. By implementing the vehicle interface, this class commits to providing concrete implementations for all 4 required methods: start, stop, accelerate, and get specifications. Even though electric vehicles use fundamentally different technology, they'll still fulfill the same contract as our conventional vehicles. I'll start with the start method. Instead of starting an engine, I'll print EV initializing electric motor. This will immediately show the fundamental difference in how electric vehicles operate compared to traditional vehicles. There'll be no engine to start, just an electric motor to initialize. For the stop method, I'll print EV shutting down electric motor. Again, this will reflect the different technology underlying electric vehicles. We won't be stopping an engine, we'll be shutting down an electric motor system. The accelerate method is where electric vehicles will really demonstrate their unique advantage. I'll print EV instant torque with electric acceleration. This will highlight one of the most impressive features of electric vehicles, which is their ability to deliver immediate power without the delay you get with traditional engines. Finally, the get specifications method will return electric vehicle specs 5-door, 5 seats electric motor. These specs will position our electric vehicle as a modern family car that happens to use revolutionary electric technology instead of traditional fuel. What'll be remarkable is that even though electric vehicles use completely different technology from gasoline vehicles, our interface design will allow them to integrate seamlessly into our system. This flexibility is exactly what makes the factory method pattern so powerful for accommodating future technologies. Now we'll reach the core of our factory method pattern implementation with the vehicle factory class. I'll create a vehicle factory class that will represent the central concept of the pattern by taking responsibility for creating vehicles without forcing our client code to know about specific vehicle classes. I'll create a public class called Vehicle Factory. This factory will centralize all our vehicle creation logic, which means that instead of scattering new sedan, new SUV, and new electric vehicle calls throughout our application, we'll have one place that handles all vehicle instantiation. Inside this class, I'll create a public method called createVehicle that will accept a string parameter called vehicle type. This method will be the heart of our factory, and it will determine which specific vehicle to create based on the type requested. I'll implement this method using Java's modern switch expression syntax, which will make the code both elegant and efficient. When the method receives sedan as the vehicle type, I'll return a new sedan object. For SUV, I'll create and return a new SUV instance. And for electric, I'll produce a new electric vehicle. Notice that I'll use vehicle type dot to lowercase to make our factory case insensitive. This means clients can request the vehicle type in any combination of lowercase or uppercase letters, and they'll all work correctly. For any unrecognized vehicle type, I'll throw an illegal argument exception with a helpful error message that includes the unknown vehicle type. This will provide clear feedback when someone requests a vehicle type that doesn't exist. This factory design will provide several crucial benefits to our system. First, I'll be decoupling vehicle creation from vehicle usage, which means our client code won't need to know about specific vehicle classes. Second, I'll be centralizing the decision-making logic about which concrete class to instantiate. And third, if we want to add new vehicle types in the future, we'll simply add another case to our switch expression without modifying any existing client code. Now we'll create the Vehicle Manufacturing System class, which will coordinate our entire vehicle manufacturing process. I'll create a Vehicle Manufacturing System class that will demonstrate how to use dependency injection to work with any factory implementation, making our system incredibly flexible. I'll create a public class called Vehicle Manufacturing System. This class will be responsible for managing the complete manufacturing process from order to delivery. First, I'll declare a private final field called Factory of Type Vehicle Factory. By making this field final, I'll ensure that once a factory is assigned to our manufacturing system, it can't be changed. This will promote stability and thread safety in our design. Now I'll implement the constructor that will accept a vehicle factory parameter. Inside the constructor, I'll assign the provided factory to our private field. This will be dependency injection in action, where I'll allow the specific factory implementation to be provided from outside the class rather than creating it directly inside. Next, I'll create the manufacture vehicle method that will take a string parameter called type. This method will represent the complete manufacturing process from start to finish. Inside this method, I'll first delegate the actual vehicle creation to our factory by calling factory.createVehicle with the provided type. I'll store the result in a variable called vehicle. Then I'll print a message that says manufacturing new plus the vehicle type plus vehicle to give us visibility into what's happening during the manufacturing process. After that, I'll print the vehicle's specifications by calling vehicle.getSpecifications. This will show us the technical details of what we've just manufactured. Finally, I'll return the manufactured vehicle object to the caller. This will complete our manufacturing process and allow the client code to work with the newly created vehicle. This manufacturing system will beautifully demonstrate the factory method pattern in action. The system won't need to know about specific vehicle types. It'll simply delegate creation to the factory and manage the overall process, making our code more maintainable and flexible. Now we'll create our demonstration class to showcase the complete factory method pattern implementation in action. The factory method demo class serves as our main entry point, bringing together all our components to demonstrate how they work seamlessly together. This demo class illustrates the power and flexibility of the factory method pattern by creating different vehicle types and displaying their distinct behaviors. Inside our main method, we begin by setting up our core components. First, I create a vehicle factory instance and store it in a variable called factory. This factory will be responsible for creating all our different vehicle types based on the requests we make. Next, I create our vehicle manufacturing system and pass in the factory we just created. Notice how I'm using dependency injection here. The manufacturing system receives the factory it needs through its constructor. This demonstrates good object-oriented design by keeping our components loosely coupled. Now I print a header that says manufacturing different vehicles to clearly separate our demo output and make it easy to follow. First, I'll manufacture a sedan by calling manufacturing-system.manufactureVehicle with sedan as the parameter. This creates our sedan vehicle, which I store in a variable called sedan. Then I demonstrate the sedan's functionality by calling start, accelerate, and stop methods in sequence. I print an empty line for clean formatting. I'll perform the same operations for the SUV and electric vehicle. Notice how the client code works entirely through the vehicle interface. It doesn't need to know the specific implementation details of each vehicle type. When we run this program, we'll see the complete factory method pattern in action. Each vehicle type will display its own distinct behavior while following the same interface contract. This demonstration validates that our factory creates the appropriate vehicle type based on input parameters, and our manufacturing system processes requests through the vehicle abstraction without coupling to specific implementations. Congratulations! You have successfully implemented a complete factory method pattern demonstrating key object-oriented design principles. This lesson covered the implementation of a vehicle interface defining method contracts for concrete classes. 3 concrete implementations were created: sedan, SUV, and electric vehicle, each providing specific behavior while maintaining interface compliance. A vehicle factory class was implemented to handle object instantiation logic, centralizing creation responsibilities. The vehicle manufacturing system demonstrates dependency injection by accepting factory instances through constructor injection. A demonstration class showcased polymorphic behavior through interface abstraction. The factory method pattern implementation achieves several architectural benefits. Object creation is decoupled from client code, reducing tight coupling between components. Creation logic is centralized in factory classes, enabling extensibility without modifying existing client implementations. Interface contracts ensure consistent method signatures across concrete implementations while allowing behavioral variance. The pattern demonstrates polymorphism through runtime method dispatch and dependency injection through constructor-based injection. This creational pattern is extensively used in enterprise frameworks, including Spring Framework's Bean Factory, JDBC Driver Manager, and various ORM implementations. The pattern provides a foundation for building scalable, maintainable, object-oriented systems. Extension points allow new concrete implementations without breaking existing functionality, demonstrating the open-close principle. The implementation showcases fundamental design patterns that form the basis of enterprise Java development architectures.